This lecture is about smoothing. Smoothing is useful when you observe nonlinear trends in data and you want to be able to predict those trends for other observations. So an important idea here is that not all the patterns that we're going to be able to model in any particular data set can be represented well by a straight line. In general, we might want to use something called smoothing, which fits a curvy but smooth line through the middle of the data to try to be able to get a better prediction. There's a risk, though, of overfitting when you use this procedure because if you fit too curvy a line that captures too well the observed data that you collected, it might not generalize well to a new data example. So we'll talk a little bit about how to deal with overfitting. It can also be hard to interpret in the sense that with a simple linear regression model, you can often interpret the coefficients on the specific terms directly in a way that makes sense in plain English. It may not necessarily be true that you can do this sort of interpretation with the smoothing functions that we're going to be fitting, so they're often more useful for prediction. The data that we're going to be using to illustrate smoothing are the CD4 data, which are available from the Data Analysis course website. In particular, we're going to be looking at two variables, the time since seroconversion, which is a particular event in the life span of a person who's infected with HIV, and CD4 count, which is a count of the number of a particular type of blood cells that fights infection. So what we can do is plot time since seroconversion versus CD4 count, and what you see is a set of data that looks like this. So I've plotted the points kind of small so that you can see all of the trends in the data, and you can see in particular that it looks like there's some kind of smooth pattern which isn't necessarily linear relating time to CD4 count. So we could just fit a linear model relating these two variables, but that might not capture all of the trend that we would like to see when we're fitting a model. So another idea is what we could do is we could fit what's called a running average. We could take the first two data points, take their average, and plot it here versus the average time point of the first two time points. We can do the same thing for the second by averaging the second and third time points and averaging the second and third values of CD4, and we get a second value like this. If we continue to do this, averaging every 2 points, overlapping by 1 each time, we get a plot that looks something like this. So you can see here that this plot is very wiggly. It goes up and down with the data very closely. And so in this case, we may have overfit the data a little bit. In other words, if we get a new data set, we don't necessarily believe all these small little wiggles to be real, whereas we might believe that this long-term trend over time might be a little bit closer to what is really going on in these data sets. So how we calculated this line is we went through and for each different data value, we averaged the time points from 2 time points before to 2 time points after that time point in question, and we did the same thing for CD4 count. For every time point I, we averaged the values 2 values before to 2 values after, and we plotted those 2 values against each other. We could average more points. So an example here is instead of averaging the 2 points before and the 2 points after, we could take each time point and average the 10 time points before and up to the 10 time points after. So now this is averaging 20 time points around the specific time point of interest, and this is averaging 20 CD4 counts around the particular time point of interest. And so what you can see is that this curve is much more smooth than the curve that we saw on the previous page because we've actually averaged more time points. So we could go even farther and make an even smoother line by averaging, say, 200 points in each direction. In other words, averaging 400 total points at each particular time point. This is the basic idea behind smoothing. What we're going to be doing is taking local averages of the data and using those local averages to represent the trend over time. A faster way to fit that same averaging that we did just a moment ago is with the filter function. So what you pass to the filter function is the time series and then what's called a filter. And the filter basically tells this function filter how to average these time points. So in this case, I've passed filter a vector that is equal to 1 over 200 repeated 200 times. So what that does is it will take the 200 time points centered on the time point that we care about, multiply them each by 1 over 200, and add them up. So that's equivalent to averaging the 200 time points, 100 to each side of the time point of interest. So in general, you can do the same thing for CD4, and so you get, again, an average of the CD4 values 100 values in either direction from the value of interest. An important thing to note here is that this works only if you've ordered the CD4 values by time. If you return to the slide where we loaded the data, you'll see that we've actually performed that ordering before we got started. So what it does is it finds each different time point, finds the 200 values that are closest in either direction, averages them, and then plots that smooth curve. This is a nice way of performing a filtered or smooth average across time. So in general, averaging is equal to doing a weighted sum. And that's what we're using when we use this filter function. So for example, if we apply the filter function to the CD4 data, and we look at the second value, this is going to be the value that averages the two previous time points with the two following time points and divides them by 4. So that basically calculates the moving average of the 4 time points immediately around the time point of interest. Similarly, we could just sum up the first 4 CD4 counts and multiply them each by 1 over 4 and add them up. What that would give us is the exact same value as what you get out of the filter function. So the disadvantage of this is that sometimes you might think that the two values that are very close to each other should contribute a lot of weight to the moving average, but values that are farther apart should contribute less weight. So here's an example of a function that you could use to create a moving average instead of just averaging each of the values equally. What I've created here are called the two key weights, and so the weight function is equal to 1 minus x squared, and then that whole value squared, and it never allowing any of the values to be negative. That's what the p max does here. It takes all of these values. If it's less than 0, it sets it equal to 0. We then let the filter be equal to, or the weights that we're going to be using when we weight the values, be equal to this two-key function applied to a particular window where the window runs from minus ws to plus ws, and we divide it by ws plus 1. We then take that filter and we divide it by its sum. The reason why is because we want the set of weights to sum to 1. There's a particular mathematical property that shows that when the sum of the weights is equal to 1 and a few other properties hold, you get a good estimate of the function when you use this smoothing. So if we plot our function, we can plot the sequence from minus ws to ws, and then we can plot the weight function. What we see is the weight function is always positive, and it runs from 0 to about 0.08, and that points near to the center get higher weights, and points farther out from the center get lower weights. So what we would do is we would apply this function and multiply it. Suppose we started at time point 0. We would apply the weight 0.08 to time point 0. Then we would move 1 unit in either direction, multiply by these weights, 1 unit in either direction, multiply by these weights, and so forth. Until we were 10 units away, we would be multiplying by a much smaller weight. So what this does is it averages points that are close to the center with higher weights and points that are farther away from the center with lower weights. We could then use that same two-key weighting function and apply it with the filter command. So again, we defined our window size here to be 100. We define the two key weights according to the function as we showed on the previous slide. Then we create the filter weights by applying two-key to the two-key function to the sequence from minus ws to ws and dividing by its sum so that the weights sum to 1. We then apply that filter using the filter command to the time data and to the CD4 data. If I plot the smooth time versus smooth CD4 data, I get what looks like here, a much smoother curve. So what that did was, it's the same thing as using the filter function with a filter equal to 1 over n repeated n times, except now what this does is it weights points that are farther away from the point of interest less. Another potentially simpler in terms of R command's approach to smoothing is called loess. Loess can be spelled either Lowess or Loess. They're actually slightly different things, loess being a slight generalization of loess with a W. These two terms stand for locally weighted scatterplot smoothing, and they're an idea that basically uses the similar sort of idea in terms of a locally weighted average of the data. You can fit a loess model using the loess command in R. This loess command takes an argument that's very similar to a linear model argument, where you have a CD4 count on the left-hand side as the outcome, a tilde, and then the covariate that you would like to fit a smooth relationship with, in this case time, and then you tell it what data set you would like that loess to come from. You can then plot the data set, just like we did before, with a small CEX so the dots are small and easily visible. And then you can add the smooth by plotting the time variable versus the loess smooth fitted values. You can see here you get a pretty smooth fit to the data. That's because the loess function does some decision making for you in terms of choosing how smooth this line should be. You can look at the arguments of the loess function if you want to learn a little bit more about how those decisions are made. If you don't want to rely on the default decisions that are in the loess function in R, what you can do is you can do something like set the span of the loess. The span relates to the number of points that are used when smoothing. So if the span is equal to, say, 0.1, then at each different data point, about 1/10 of all of the data points are used in calculating the local weighted value for that data point. If the span is equal to 0.25, then about 1/4 of the data are used for calculating that smooth value. And if the span is equal to 0.76, then about 3/4 of the data are used when calculating the smooth value at any point. As the span increases, you'll see that the line becomes more smooth. In general, this means that the line may be more biased because we're smoothing it more and more, but it will be less variable in the sense that it's a more stable fit to the data when you smooth over more of the data in general. So what you can see here is the span is 0.1, the blue line is quite wiggly. When the span is 0.25, it gets less wiggly with the red line here. And when the span is 0.76, the line is quite smooth, almost as smooth as you saw on the previous slide. So what you can do is actually choose your own span variable by hand, or you can rely on loess to calculate the span for you. With the loess function, we can actually predict new values. So if I generate a new variable, TME, that is a sequence from -2 to 5, I can predict the values of that sequence using the loess object I calculated on the previous slide, and giving it a new data frame that gives the time variable as the TME values. Here I'm setting the standard error equal to true so that it calculates the standard error of the predictions. I can then plot time versus the fitted values. That's what you see in this blue line here. And I can also fit the values of the prediction intervals. So in this case, I plot TME, the TME values, versus the predicted values, plus 1.96 times the standard error of the fit. I can also do the same thing minus 1.96 times the standard error of the fit. It's kind of hard to see in this plot because it's small, but if you make this plot in your own R window, you'll see that near the edges of the boundaries, the prediction intervals are actually wider than they are in the center. That's because you have less data out here, so it's harder to make accurate predictions. One more type of smoother that I'm going to be talking about is called splines. The reason why I bring up this type of smoother is because it's easier to use when you want to adjust for more than one covariate in your model. So suppose you only want to fit one smooth variable and relate it to an outcome. So you have an outcome variable yi for observation I, which is equal to an intercept term b0 plus a sum of terms where you have a coefficient times a function applied to the covariate xi. So you might imagine these functions could just be the functions like x, x squared, x cubed, or they could be more complicated functions. Either way, you're going to apply multiple functions to each data point, weight them by these coefficients bk, and add them up. Then there's the error term, which represents everything we didn't measure or model. One popular choice are natural cubic splines. So if you load the library Splines and you calculate the natural cubic splines for the time data, you have to tell it the number of degrees of freedom that you'd want. The number of degrees of freedom is equal to the number of functions that will be applied to the time variable. So if I plot, the result will be a matrix where each column of that matrix is equal to one of the functions. So I can plot each of the functions one by one, and what I get in this case are three functions that look a little bit strange. They're three smooth looking functions that look like this. Now what I'm going to do for any data point is multiply. Suppose I'm going to calculate the data point for time 0. What I'm going to do is multiply the value of this function at time 0 times its coefficient plus the value of this function at time 0 times its coefficient plus the value of this function at time 0 times its coefficient plus the intercept term, and that will give me the new fitted value. So the nice thing about using these splines is that you can include them in a linear model just like this. So if we have the CD4 count as the outcome, we then use the tilde, and on the right hand side, instead of our covariates, we include our spline matrix. So the spline matrix, remember, is the set of three functions applied to the time points. So this is actually only one variable that I've included in the right hand side, but that variable has now been has had three different functions applied to it. What you get out is an estimate of the intercept and then a coefficient for each of the three spline functions. Now, as I mentioned at the beginning of the talk, interpreting these coefficients for these specific spline functions is difficult and is not necessarily recommended. But the cool thing is if you plot the fitted values, you actually see that they represent this smooth curve. Even though we use those three strange functions, when you multiply them together and add them with their coefficients, you get actually a very nice fit to the data. In general, using splines will allow you to get a very flexible fit to the data, and the degrees of freedom is equal to about the polynomial that you would imagine that it would take to fit this type of data. So in this case, we've set degrees of freedom equal to 3, and this looks like about a third order polynomial for people that remember what a third order polynomial looks like. An important point here is we just used the term ns1 in the linear model just like we would any other regression coefficient. So we could include other variables if we'd like to adjust for them in this linear model in addition to the smooth terms. That's an advantage of using splines when doing smoothing of a specific variable, but you might not want to smooth all of the other variables. So a little bit on notes and further resources. You might want to do cross-validation when you're using splines or smoothing, and the reason why is you might get overfitting, particularly if you use a very small span or you do a weighted average with only a very small number of points. Try not to predict outside the range of the observed data, because even with very smooth functions, once you get outside of the observed data, you can get really dramatic differences in what the prediction is and what the reality is likely to be. Some further resources and notes are Hector Curata Bravo's and Rafa Irizarry's lecturings on smoothing and on splines. The elements of statistical learning and advanced data analysis from an elementary point of view also have a very nice set of information about smoothing.